From Newton to Turing, A Happy Family. A sermon by Pastor Manuel Laproig, Doctor of the Divine.
Academics should just marry Turing completeness already.
The Grunk. When engineers first gifted humanity with horseless carriages that moved on rails under their own power, this innovation, for all its usefulness, turned out to have a big problem. Occasional humans and animals on the rails. This problem motivated many inventors to look for solutions that would be both usable and effective. Unfortunately, none worked. The reason for this is not so easy to explain. At least Aristotelian physics had no explanation, and few scientists till Galileo's time were interested in one. On one hand, motion had to be brought by some force, and tended to kind of barrel about once it got going. On the other hand, it also tended to dissipate eventually. It took about 500 years from the doubting of the Aristotelian idea that motion ceased as soon as its impelling force ceased, to the first clear pronouncement that motion in absence of external forces was a persistent rather than temporary virtue. And another 600 for the first correct formulation of the exact quantities of motions that were conserved. Even so, it took another century before the mechanical conservation laws and the actual names and formulas of motion and energy were written down as we know them. These days, conservation of energy is supposed to be one of those word combinations to check off on multi-choice tests that makes one eligible for college. Yet, we should remember that the steam engine was invented well before the laws of classical mechanics were comprehensible, or even understood at all. Moreover, it took some further 40 to 90 years after Watt's 10-horsepower steam engine patent to formulate the principles of thermodynamics that actually make a steam engine work, and by which time it was chugging along at 10,000 horsepower, able to move not just massive amounts of machinery, but even the engine's weight along rails, plus a lot more. All of this is to say that if you hear a scientist doubting an engineer can accomplish things without their collective guidance, they have a lot of history to catch up with, starting with that thing called the Industrial Revolution. On the other hand, if you see engineers trying to build something that just doesn't seem to work, you might just be able to point them to some formulas that suggest their energies are best applied elsewhere. Distinguishing between these two situations is known as magic, wisdom, extreme luck, or divine revelation. Whomever claims to do so unerringly is at best a priest, not a scientist. There is an old joke that whenever an activity needs to add science to its name, it's not too sure it actually is one. Some computer scientists may not take too kindly to this joke, and point out that it's actually the word computer that is misleading, as their science transcends practical silicon and copper designs. It is undeniable, though, that hacking as we know it would not exist without actual physical computers. As scientists, we like exhaustive arguments, either by full search of all finite combinatorial possibilities, or by tricks such as induction that look convincing enough as a mean of exhausting infinite combinations. We value, above all, being able to say that a condition never takes place or always holds. We dislike the possibility that there can be a situation or a solution that we can overlook, but someone may find through luck or cleverness. We want yes to be a yes, and a no to mean no way in hell. But either full search or induction only apply in the world of ideal models. Call them combinatorial, logical, or mathematical. That excludes any kind of unknown unknowns. Hence we have many models of computation, substituting strings into other strings, Markov algorithms, rewriting formulas, lambda calculus, automata with finite and infinite numbers of states, and so on. The point is always to enumerate all finite possibilities, or to convince ourselves that even an infinite number of them does not harbor the one we wish to avoid. The idea is roughly the same as using algebra. We use formulas we trust to reason about any and all possible values at once. But to do so, we must reduce reality to a set of formulas. These formulas come from a process that must prod and probe reality. We have no way of coming up with them without prodding, probing, and otherwise experimenting by hunch and blind groping. That is, by building things before we fully understand how they work. Without these, there can be no formulas, or they won't be meaningful. So, here we go. Exploits establish the variable space. Science searches it, to our satisfaction or otherwise. Or, importantly to save us effort, asserts that a full and exhaustive search is infeasible. This may be the case of energy conservation versus trying to construct a safer fender, or perhaps the case of us trying to formulate what makes sense to attempt. That which we call the arms race is part of the process. With it, we continuously update the variable space that we wish to exhaust. Without it, none of our methods or formulas means much. This brings us to the recent argument about exploits and Turing completeness. Knowledge is power. In the case of the steam engine, the power emerged before the kind of knowledge called scientific, if one is in college, or basic, if one is a politician looking to hitch a ride, because actual science has a tradition of overturning its own basics, as taught in schools, for at least decades, if not centuries. In any case, the knowledge of how to build these engines was there before the knowledge that actually explained how they worked, and would hardly have emerged if these things had not been built already. Our situation, neighbors, is not unlike that of the steam power before the laws of thermodynamics. There are things that work, pump mines, drive factories, and there are official ways of explaining them that don't quite work. Eventually, they will emerge, and the explanations will catch up, and then become useful for making things that work better. But they haven't quite yet, and it is frustrating. The situation is understandable. As soon as academics rediscover a truly nifty kind of exploit programming, they just not focus on the least practically relevant aspects of it, Turing completeness, but do so to the exclusion of all other kinds of niftiness, such as information leaks, probabilistic programming, heap feng shui and spraying, parallelism, cloning and pinning of threads to sap randomization, and so on. That focus on the irrelevant to the determinant of the relevant had really rankled. It was hard to miss where the next frontier of exploitation's hard programming tasks and its next set of challenges lay. But, oh boy, did the academia do it again. Yet, it is clear why they did it. Academic CS operates on models and exhaustive searches or reasoning. Its primary method and deliverable is exhaustive analysis of models, i.e., the premise that certain bad things never happen, and that all possible trajectories of a system have been or can be enumerated. Academia first saw exploit programming when it was presented to them in the form of a model. Prior to that, their eyes would just slide off it, because it looked ad hoc, and one can neither reason about ad hoc or enumerate it. At least if one wants to meet publication goals. When it turned out it had a model, academia did what it normally does with models. Automating, tweaking, searching, finding their theoretical limits and relating them to other models, one paper at a time. It's not a bad model. At least it gave us complex compilers and CPUs that didn't crumble under the weight of their bugs. Eventually we will want this kind of assurances this model creates. When their model of unexpected execution are complete enough and close enough to reality. For now, they are not, and we have to go on building our engines without guidance from models, but rather to make sure new models will come from them. Not that we are without hope. One only has to look at Grescurity/PaCs at any time to see what will eventually become the precise stuff of Newton's law for better OS kernels. Similarly, the inescapable failure modes of data and programming complexity will eventually be understood, as clearly as the three principles of thermodynamics. Until then, our best bet is to build engines, however unscientific, and construct theories, however removed from real power, and hope that the engineering and the science will take enough notice of each other to converge within a lifetime, as they have had the sense to do during the so-called Industrial Revolution, and a few lucky times since. And to this, neighbors, the pastor raises not one but two drinks. One for engineering orienting the science, and one for the science to catching up with the real knowledge that is power. and saving it from the efforts that cannot be done. And may they ever converge. Amen.